Hi everyone, in this video we're going to give a beautiful example of a function that is differentiable but its derivative is not continuous. And watch till the end to see why this example is in fact mind-blowing and satisfies a remarkable property. So what I'm going to do is I'm going to explain what the example is first of all. So our function f of x, it's going to have the following property. It's going to be x squared times sine 1 over x. It's piecewise defined when x is not equal to 0. And when x is equal to 0, our function is just going to be 0. Okay, so at x equals 0, our function is just going to be 0. This is our f of x, and we're going to prove that f is differentiable, but its derivative is discontinuous at 0. Okay, so before we actually get into it, first let's try to just look at why f is differentiable. That's the first step. So f is when x is non-zero, it is a composition of differentiable functions in sine 1 over x. 1 over x is differentiable, sine 1 over x is differentiable, and then you multiply with another differentiable function. So it is differentiable for non-zero numbers. The real challenge is why it's differentiable at x equals 0. So to illustrate why this is actually not that or quite subtle is we just try to find a formula for the derivative of f when x is non-zero. So when x is non-zero, we can differentiate f using the product rule and the chain rule. First differentiate x squared, which is 2x, multiply by sine 1 over x. Then we add on, using the product rule, x squared times the derivative of sine x, sine 1 over x. So what is the derivative of sine 1 over x? It is cos of 1 over x, differentiate the outside first, so you get cos of 1 over x, multiplied by the derivative of what's inside, which is minus 1 over x squared. Because the derivative of x power minus 1, or 1 over x, using the power rule is minus 1 x to the minus 2, which is minus 1 over x squared. So here we're going to get this expression, and if we actually expand this out, okay, we get 2x times sine 1 over x, but also the x squared and the minus 1 over x squared, they cancel to give a minus 1, so we get minus cos of 1 over x. Now the issue here is that if you take the limit as x goes to 0 of f prime of x, you are not going to get something that's well defined. Okay, so that's number one, because we're going to actually go through that in detail, but you cannot actually say f prime of 0 is this formula plugged in for 0 for two reasons. First of all, this formula plugged in at x equals 0 doesn't even make sense. You can't divide by 0. Second of all, we have just differentiated f when x is non-zero. So we can't actually say this is the derivative at 0 just by plugging in x equals 0, because this is only applicable for x non-zero. So what we're going to have to do to differentiate f at 0 is we're going to use the original definition of the derivative using limits. And this is how, strictly speaking, even this whole product rule and chain rule comes from that via a series of theorems. The product rule, the chain rule, the derivative of trig functions, the power rule, etc. But really everything boils down to the limit definition of the derivative, which is f prime of 0 is basically the rate of change of f at 0. It's f of h minus f of 0 divided by h. Change in y over change in x. And now we can plug in this into this formula what f is. So we're going to get limit h goes to 0 of f of h is going to be h squared sine 1 over h. And of course, f of 0 is just going to be 0. That is a definition. So that is the piecewise definition, right? We have to define f to be 0 at 0 because that formula won't work for x is 0. So we have to define f piecewise. And then we're going to divide this by h. And this is now going to be limit h goes to 0 of h times sine 1 over h. Now I have a video, it's quite popular on my channel, based on my lectures at Princeton University, where I explain the sandwich theorem. This is what governs limit h goes to 0 of h sine 1 over h, and I really encourage you to watch that video to get a deep understanding from various angles of that theorem. You'll be a master of that theorem after seeing the video, but the basic idea is that when you think about this limit, as h goes to 0, sine 1 over h oscillates wildly, because 1 over h is going to go to plus minus infinity depending on how h approaches 0, and sine is just going to oscillate from minus 1 to 1. So this limit sine 1 over h, if you forget the h, is going to be undefined, doesn't exist. But the h itself is going to approach 0. And the idea here is that 0 times something that doesn't exist is 0, because the sine 1 over h doesn't go to infinity. You don't have an indeterminate form like 0 times infinity. You have something that's a number between minus 1 and 1. So if you multiply it by something very small, it's going to approach 0. That's the intuition, but check out that video to really deeply understand it, okay? So here this is going to be 0. The total limit is going to be 0. That's what's explained in that video, and I summarized here. And that shows that f prime of 0 is 0, straight from the definition, okay? So what we've now found is we found a formula for f prime, because we found out what f prime of x is for x non-zero, and we found out f prime of 0 is 0. And that's now the argument almost, because The next point is, now that we've seen that f prime of 0 is 0, we now know that f is differentiable, okay? So it's a differentiable function, but its derivative is not continuous. Why is it not continuous? Well, it's perfectly fine and continuous everywhere that is a non-zero number. You know, it's given by this formula, which is a composition of continuous functions. As long as x is non-zero, this is continuous. But the limit, even though f prime of 0 is 0, as we just saw, the limit as x approaches 0 of f prime of x is going to be the limit as x approaches 0, and I'm going to be super rigorous here, okay, so you deeply understand why this is true. It's going to be the limit as x approaches 0 of 2x sine 1 over x minus cos of 1 over x. So why does this limit not exist? Okay, so it's very important here. We cannot say that, okay, just because the limit of cos 1 over x doesn't exist, therefore the total limit doesn't exist. You can't do that. Why is that? Well, I can show you something really dumb, which I'm going to mark in red. It's not true that just because one summon the limit doesn't exist, therefore the other doesn't exist. For example, I can say limit h goes to 0 of cos of 1 over h minus cos of 1 over h. Okay, and here of course this is 0 because you're just subtracting something from itself. So you can't just say, okay, because this doesn't exist, therefore the whole limit doesn't exist. We have to use the fact, it's a proof by contradiction if you want a mathematical proof. If this limit existed, okay, if this limit existed, by limit laws, you could subtract the limit as x approaches 0 of 2x sine 1 over x. And that limit would also exist. Because if two limits individually exist, the limit of the difference is the difference of the limits. So if, for a contradiction, if this limit existed, we could then subtract off 2x sine 1 over x because we know that limit existed. We just used that to find f prime of 0. We know that limit is 0. To therefore conclude that the limit of h approaches 0 of simply cos 1 over h exists. Okay, so we could use that argument that I just gave to say that if it existed, that would mean that limit x approaches 0 of cos of 1 over x existed, and that we know does not exist for the same argument I gave. Cos oscillates between minus 1 and 1, and as x approaches 0, 1 over x goes to plus minus infinity, so it's oscillating. Okay, so it just doesn't approach any number. It just approaches anything between minus and 1 in some sense. So it doesn't really approach anything. So this doesn't exist, so therefore this also doesn't exist. So f prime is discontinuous at 0. I'm going to tell you something mind-blowing right now. Before I do that, I'm going to show you the graph of the function very intuitively. So the graph of this function x squared sine 1 over x, which also explains, you know, all the stuff we've just seen, okay, very visually, because I really like doing things both algebraically and visually. So we know that, this is a point I've alluded to many times in this video so far, that minus 1 less than or equal to sine 1 over x less than 1, right? So we know that, so therefore what we can do is, we can bound, we can multiply by x squared on both sides. X squared is always a non-negative number, so it doesn't reverse the inequality, okay, unlike multiplying by x. So you could say therefore minus x squared is less than or equal to x squared sine 1 over x is less than or equal to plus x squared. So now we can graph x squared sine 1 over x to really see what this function looks like. What's going to happen is you're going to have these parabolas y equals x squared, okay, which I'm going to draw like this. There's a parabola y equals x squared, and then a parabola y equals minus 1 over x squared, and then the point is that our function x squared sine 1 over x, because of the oscillation, is just going to oscillate wildly, okay? It's just going to oscillate wildly, but it's kind of juiced between these two parabolas, okay? It's kind of like squeezed between these two parabolas, okay? And then what happens is that's our graph of our function. That's the graph of the function f of x, and we are defining it at 0 to just be 0, okay? So that's the graph. And it's really cool because if we just had x sine 1 over x, it would not be differentiable at 0. So I want you to explain, drop a comment down below, why if we remove the square, this function would not be differentiable at 0, okay? Even though the graph will look very similar. Here it's somehow because it's squeezed between two parabolas rather than lines that makes it differentiable at 0, but its derivative still fails to be continuous, okay? And why this example is so mind-blowing is because it's very hard to make derivatives discontinuous. In fact, there is a theorem in math that if you have a function and it's differentiable everywhere, its derivative has to be continuous on a dense G delta set of numbers. And if you don't know what that is, don't worry. It just means a very, very large number of numbers, okay? In some sense, very intuitively, like almost all numbers in some sense. So it's very hard to create discontinuities at lots of points. In fact, there is no example of a function that's differentiable whose derivative is discontinuous everywhere, or even discontinuous on a reasonably large set. it has to be discontinuous only on a somewhat small set, okay, in some vague sense. So that's going to be maybe the topic of another more advanced video, and subscribe to my channel for lots more advanced math. I don't just do calculus, I do real analysis too, which is the rigorous mathematical way of looking at calculus that high-level mathematicians do. And so once you learn calculus, or simultaneously, you can watch those videos and learn from them. Also, please check out my video where I explain the sandwich theorem, which I used here to show that f prime of 0 was 0. Check out that video, it's explained in depth based on my lectures at Princeton University. It's gonna pop up here. I'm gonna see you in that video. Wish you all the best. See you there.